Hello and welcome to this video on caching in web services. So let's begin by talking about caching. What is caching? Caching is nothing but retaining a copy of data so that future requests for that data can be served faster. The data that's stored in a cache could be results from an earlier computation or could be duplicates of data that has been stored elsewhere. So that's the basic idea of caching in general in computing. Let's take a quick look at examples of caching that you might be familiar with, that is caching that happens within a single machine. So let's look at some of the storage devices inside a computer. First, we have CPU caches and registers. These are on-chip, on-die memory that's available with CPUs. This can range from multiple kilobytes to megabytes. They're very expensive. The technology used is usually called SRAM or static RAM. But they're also very fast. Their average latency is between 1 and 5 nanoseconds, and their latency can be measured sometimes in clock cycles of the CPU. So items that are fetched from registers can be typically done in a single clock cycle or a few tenths of a clock cycle, for example. And as you go up the tiers in CPU caches from L1 through L3 cache, the latency will start increasing. Next in the storage devices, we've got main memory, also known as DRAM. Now, this can range from 4 gigs to about a terabyte in size these days. Typically, having a terabyte of memory is reserved for high-end servers, but it is possible. And this kind of memory costs about $10 per gigabyte, so it's a lot cheaper than registers and CPU caches. As you can see, it's just many orders of magnitude cheaper. But you also increase the latency by an order of magnitude. So depending on the type of RAM technology used, your latency can differ from 10 to 50 nanoseconds. Further down, we've got solid state drives. You can get solid state drives ranging from 64 gigs to 1 terabyte in size. And they cost about $2 a gigabyte. But as you can see, the latency suffers quite a bit because now your latency to fetch data is anywhere between 50 to 150 nanoseconds. Then we have conventional magnetic hard drives, which are slowly losing ground to SSDs as SSDs become more dense and cheaper. But magnetic hard drives are still quite cheap. I mean, sort of the minimum size that you get these days are 1 terabyte, and you can get single magnetic hard disks that are up to 6 terabytes. And of course, you can employ some kind of system like RAID or use magnetic hard disks in a big SAN, and you can get terabytes or even petabytes of storage. And it's relatively cheap because it's 4 cents per gigabyte approximately. But as you can see, the access time is increased significantly. We're no longer talking about nanoseconds here. This is in the millisecond range now, and it's about 5 to 10 milliseconds. Finally, we've got remote secondary storage, stuff that's on the cloud, that's offline, that's in tape backups, that's on CD-ROM, etc. Now, this stuff is virtually infinite and virtually free in terms of its capacity and in terms of size, but at the same time, this stuff is very, very slow. So fetching something from the internet or through a cloud is greater than hundreds of milliseconds long, depending on the size. The same can be said for any kind of offline data that's on removable storage. It just takes a long time compared to the time it takes for a CPU to fetch something from a register. It takes like eons if you look at it from that scale. So now we have an idea of the storage devices that are involved in computation. And the idea of caches is that you progressively copy data from one tier to another as they're being used, and you always retain some of that data in the different tiers so as to enable future computation to run faster, much faster, in fact. The question then comes up on, well, how do you decide how you're going to choose what data to keep in each layer and what data to sort of discard? And the idea here in caching basically boils down to locality. There are two types of locality that most caches use. I'll be discussing the first one, which is temporal locality. So imagine you had a CPU that's interacting with main memory, and the CPU issues an instruction to fetch a particular address of memory, DEA, BEF, for example. The main memory then looks up that particular address, fetches the data item, and then copies it back to the CPU, where the CPU keeps that data in cache. Now, the idea is the CPU just asked for that address. So it's very likely that a future instruction may ask for that address again. This is the principle of temporal locality. So if you notice in the future, a few, instructions later, or maybe a few seconds later, there may be another instruction that asks for the exact same address. And since this address is available on the CPU cache, it can be retrieved much faster than from main memory just by copying it off of the cache. So this is the idea of temporal locality. The fact that you've accessed a particular data item at a particular point of time means that it's highly likely that you will ask for that same data item in the near future, hence temporal, time-based. The other idea in caching is spatial locality. Now, spatial locality is similar to temporal locality, but it's on a different dimension. It's in the space dimension, not in the time dimension. So the idea here is if the CPU asks for a specific memory address for some specific data, the same example again. Now what happens is the main memory doesn't copy just a single data item to cache. In fact, it'll copy an entire block of all of the nearby data items to that memory address and copy the entire block to the CPU cache. Now, you need to remember that both of these properties are not mutually exclusive of spatial and temporal locality. In fact, many CPU or other caches, in fact, use a combination of both the ideas of temporal and spatial locality to manage caches, to make sure that you have the correct data items available for future requests so that they can be sped up. And this is quite important in keeping computation at a high performance, is to have very well-tuned, well-designed caches almost at every stage. So in this particular example, I spoke only about CPU and memory, but in fact, there are various versions of caching available even further down the memory hierarchy. So for example, the concept of virtual memory is also an idea of a cache where you keep data paged in disk, and as pages are being requested by the CPU, move pages from disk to main memory, and inactive pages go back to disk. So that's also an idea of a cache, basically. So, and like I said, any future requests for the data will be available. So let's look at caching in web services. So we're going to step away from a single machine and talk about, in general, a web architecture with clients and servers. How do you use caching in this respect? So let's take a look at a simple example. Let's think of a service in which you have a client and a website. And in fact, the website is a kind of like a Twitter service. Something like Twitter, it just keeps, status updates for each of its users. So this client may request a particular tweet from the web service. So this is going to be formatted as an HTTP request. In this case, I'm going to ask for the status of a user called Obama. I'm asking for the particular status number 123124, and I'm directing it to tweets.com. So there are many ways in which this request could be handled. You could have a load balancer, or you could have some sort of a DNS round robin system. But whatever it is, we've got some kind of mechanism to distribute the load among multiple web servers. So this request is then forwarded to one of the web servers in our pool of web servers. Now, the web server would take that request and use its logic to convert it to a database query, because we're in this particular instance, all of our data is stored in databases, right? So the idea then would be, okay, the web server now translates that client request into some kind of database request. And here on screen, you can see I have a SQL query which translated that HTTP request to an actual SQL query asking for the status from a table called tweets, looking for a particular username and asking for a particular tweet ID. What the DB can do is then, reply with the answer. And just like our CPU cache, our web servers can actually keep this database reply in a cache so that it doesn't always have to go back to the DB backend and make a request again for every client request, right? And then obviously this reply is sent back to the client. The idea is if another client, and in this example, it's not just browsers, but it could also be mobile apps that's making, these requests to web servers. Another client comes up, shortly afterwards and makes the same request. Now the web server can simply reply from the cache and not have to go to the DB backend to retrieve that particular, tweet, and it can just simply reply back to the client directly. So let's look at a few other types of caches apart from the example that I spoke about just now. Well-engineered client applications typically have some kind of client-side cache. Now, in this mechanism, if you're in a web browser, you use some kind of AJAX or dynamic web technology, like some smart JavaScript that sort of looks at the user's actions on the page and then preemptively makes requests and caches them on the device itself, whether it's the browser or a mobile phone. It's a sort of, a mix of temporal and spatial locality. And a good example of this is, someone who's going through a photo album, say on Facebook or any other kind of social media. As the user is browsing through the pictures, the client-side JavaScript can actually prefetch some of the future photos in the album in order to make that experience as fast as possible. So it would actually prefetch and keep a copy of the data that is anticipated by the user, right? And other caching mechanisms are available. Web browsers themselves cache a lot of data and images, for example, in their browsing history, basically. So that's another idea. That's sort of like an automatic type of cache that works to keep content on the client and in order to improve performance and the speed of browsing. And then there's the idea of caching tiers. So there was more complex custom web architectures that are available. And the idea here is, well, you design a complicated caching tier architecture and you can keep data in various levels of cache based on temporal locality, moving data between storage devices as they get more popular or more stale. So a good example and a good paper to read if you're interested is something called the Facebook warm storage system. So as new media such as photos and video get published, especially by people like celebrities, it's available on a higher state of cache. But as time progresses, the Facebook engineers actually looked into the statistics of this and found that on average, within 2 or 3 weeks, something that is a very hot item of content, like a photo or a video, sort of dies down within a few weeks, and then it can be safely moved off to a much slower storage system in order to keep in order to keep hot items at the fast storage system, so you make space for newer items. But at the same time, the data item is always available. It just takes a little longer to fetch or retrieve.